Okay, so now I'm going to go over the steps of showing when a polar curve is symmetric and what kind of symmetry it has based on these steps using polar coordinates. Okay, so we're going to consider a curve generated by the function r equals f of theta in polar coordinates. So one, the curve is symmetric about the polar axis if for every point r comma theta on the graph, the point r comma negative theta is also on the graph. So in other words, if f of negative theta is the same as f of theta, then we have symmetry. Okay, and it's symmetric about the polar axis. Okay, so the polar axis, remember, is the positive y-axis. Okay, so now, 2, the curve is symmetric about the pole. So this is again similar to the origin, right? The pole is the origin using the Cartesian plane, but in the polar coordinate system, it's called the pole. So the curve is symmetric about the pole if for every point r comma theta on the graph, the point r comma theta plus pi. So again, that's 180 degrees, right? Pi is 180 degrees, is also on the graph. In other words, if f of theta is unchanged when you replace r with either negative r, or if you replace theta with theta plus pi. Okay? 3, the curve is symmetric about the vertical line, theta equals pi over 2, so that's the positive y-axis, okay? So the curve is symmetric about the vertical line, theta equals pi over 2, if for every point r comma theta is on the graph, r comma theta, or excuse me, pi minus theta is also on the graph. So that's again symmetric with respect to the line theta equals pi over 2. Okay, so again, so we're going to do some examples of how we show that a particular function is symmetric with respect either to the polar axis, the pole, or the line theta equals pi over 2. Okay, that'll be next. See you then.